Hello everyone, I'm here to introduce our research titled Memory-Based Controllers for Efficient Data-Driven Control of Soft Robots. Conventional robotic systems suffer from poor adaptability and flexibility. Soft robots can solve the adaptability and flexibility issues of rigid robots. However, the deformation of soft robots is always nonlinear, and they have infinite degrees of freedom. These facts render the motion planning and control of soft robots a challenging task. The data-driven approach is a promising solution to the controller design problem for soft robots. However, the existing data-driven controller design methods for soft robots suffer from two drawbacks. The first one is that they require excessively long training time. And the second one is that they may result in potentially inefficient controllers. We trained the following three reinforcement learning algorithms to control a pneumatic soft finger using SOFA. The figure shows the mean reward of these three algorithms for different episodes, where each episode had 400 samples. We adjusted the layers and the neural network activation function for each algorithm to achieve the best performance. As the figure shows, even after 250 episodes, the three algorithms don't find a desirable controller. This observation suggests that the data-driven control of soft robots can be slow and may result in poorly performing controllers. The observation further motivates us to design fast, data-driven algorithms for designing accurate controllers for soft robots. We address these issues by developing two data-driven memory-based controllers for soft robots. Finite memory controller approach and the long short-term memory-based approach. The trajectory tracking problem aims to design a control input that allows a robot to follow a predefined reference trajectory, as shown in the figure below. In this figure, U sub t is a control input. PT and PT are the actual configuration and the desired configuration at time t respectively. However, as we mentioned before, since soft robots are made of flexible material, they have infinite degrees of freedom, and their deformation is always nonlinear. At the same time, the behavior of the soft robots doesn't follow from the classical solid mechanism. Thus, compared to the rigid robots, the trajectory tracking of soft robots is more complex and difficult. In this section, we develop a trajectory tracking framework for soft robots based on FMC. The figure shows the structure of an FMC with key memory units. At time t, the input to the controller is the tracking error E sub t. As shown in the right figure, the controller uses the current error and the past key errors, which are stored in its memory, to compute the required inputs of the actuators to track the desired trajectory. The output of an FMC is the weighted sum of the current and past errors. The weights of the controller are computed by solving the following optimal control problem. We next propose three algorithms for computing the optimal weights of an FMC using the following algorithms. The first one is Deep determin is a deep deterministic policy gradient. The second one is the deep Q network, and the third one is the soft actor critic algorithms. In this section, we first build an inverse model for a soft robot using an LSTM neural network. We will then use the inverse model to build an open loop and closed loop controllers for trajectory tracking. This figure shows an LSTM-based inverse model, which is made of a number of LSTM layers. The input of the inverse model is the current configuration of the robots and its configuration in the next time step. The output of the inverse model is the required control input. For the robot to change its configuration from P sub t to P sub t plus 1. This figure shows the structure of the inverse model. The input to the inverse model is the current configuration of the robot and its configuration in the next time step. In this section, we use the LSTM-based inverse model to develop an open-loop trajectory tracking controller, as shown in the figure. At time t, the inputs to the controller are the current desired configuration, P sub t to the d, and the next desired configuration, pt plus 1 to the d. The controller computes the required actuation signal for moving the software robot from the current configuration to its next configuration. The open-loop controller provides a simple solution for trajectory tracking, as it doesn't require sensing the position of the software robot at each time step. However, it's not able to compensate for disturbances and model uncertainties. In this section, we construct a closed-loop trajectory tracking controller using the LSTM-based inverse model, as shown in the figure below. The inputs to the controller are the current configuration of the software robot measured by a sensor and its next desired configuration. Using these inputs, the controller computes the actuation signal required for moving the robot from its current configuration to the desired configuration at time t plus 1. In this section, we study the performance of the proposed trajectory tracking frameworks in controlling the tip of a pneumatic soft finger in SOFA. We modeled a pneumatic soft finger using the SOFA simulation framework as shown in the figure. In our simulation environment, the soft finger can only move in a plane. Thus, to simplify the controller design, we use the angle between the tip and the base of the finger, theta k, to simplify the position of the soft finger's tip at time step k. The objective of a trajectory tracking controller is to ensure that the tip of the finger follows a desired reference trajectory, shown in the figure right. These figures show the performance of the FMC with DDPG, DQN, and SAC algorithms. According to the figure, the FMC with DDPG can accurately track the reference trajectory. Moreover, the FMCs with DQN and SAC are capable of tracking the reference trajectory, but these controllers result in fluctuations around the reference trajectory due to the stochastic nature of these algorithms. The tracking error of the FMC with different reinforcement learning algorithms is shown in the figure. According to these figures, the maximum error of FMC with DDPG is around 0.04 degrees, while the maximum tracking errors of FMC with DQN and SAC are around 1.5 degrees and 5 degrees respectively. This observation confirms that FMC with DDPG achieves the best tracking performance. We next compare the training performance of the FMCs with that of traditional RL algorithms. These figures show the mean reward every training episode for FMCs and the mean reward of standard neural network controllers. The first figure shows the tracking results of the open loop LSTM based controller, and the second one shows the corresponding tracking errors. According to the figures, the open loop LSTM based controller cannot accurately track the reference trajectory when the reference trajectory changes rapidly. Well, this figure shows the tracking error of the closed loop LSTM based controller and that of PI controller. We adjusted the parameters of the PI controller to achieve the best tracking performance. According to this figure, the closed loop LSTM based controller can closely track the reference trajectory even when the reference trajectory changes rapidly. Moreover, the steady-state error of the LSTM-based controller is close to zero. We finally compare the performance of the closed-loop LSTM-based controller. An FMC trained with DDPG and a PI controller with optimal gains in this figure. According to this figure, the FMC with DDPG achieves the best tracking performance with a tracking error close to zero. This table summarizes the average tracking error of the different controllers. According to the table, the FMC with the DDPG algorithm achieves the smallest average tracking error, followed by the closed-loop LSTM-based controller. Besides, the finite memory controller used much less training data, only 400 samples, while the closed-loop LSTM-based model used 20,000 samples for training. In this paper, we developed LSTM-based inverse models and finite memory controllers for trajectory tracking for soft robots. We also studied the performance of the developed controllers using a pneumatic-driven soft finger in SOFA simulation environment and compared the performance of the developed controllers with that of traditional RL-based controllers and PI controller. According to our results, The closed-loop LSTM-based inverse model and FMC with DDPG achieve the best performance in trajectory tracking. The link of our paper is shown here, and there are more details about our work. Welcome to read the paper and give your comments. That's all of my reports. Thanks for your attention.